So today's lecture, we're covering the ideal gas law, thermodynamic processes and cycles, the first and second laws of thermodynamics, and engines and refrigerators. And we'll do a review afterwards and finish Lab 2. Lab 2 is pretty short. It's the second experiment. It shouldn't take you guys more than 15 minutes, honestly, to collect your data. So that makes up for the fact that it's a lot of slides to cover. But the reason it's a lot of slides is because I incorporated the multiple choice questions in this lecture. Since you won't see that before the midterm, I want you to get a chance to practice some of these conceptual type problems that might show up on the midterm for this topic. So, okay. So from last week, you wish to increase the temperature of 1 kilogram block of a certain solid substance from 20 degrees to 25 degrees Celsius. The block remains solid as its temperature increases. To calculate the amount of heat required to do this, you also need to know what?
What's good?
Okay, so anybody need more time? A couple more people? Okay. All right, so who thinks the answer is A? Most people. Who thinks it's B? Who thinks it's C? Think it's D. Oh, one vote for C. Any votes for D? Anyone vote for E? All right, so tell me, what information are we given in terms of variables? Mass. Change in temperature. And since we're told that it stayed solid the whole time, what equation do we use to solve for heat in this case? Yeah, Q would be MC change in T. So the only thing we don't know is this C, and so we have to remember what is C called? Specific heat, yeah. So that, if you're shaky on the terminology, I always mention this, a really good idea to have on your one sheet of notes for the exam is like a table of terms, like variables, what they're called, when you might use them, whatever things that you commonly forget. You don't really need a whole lot of equations because I give you every equation you need. But if this is an area of difficulty for you remembering terminology, then consider putting that on your one sheet of notes.
You just have to be careful because some of these letters come into the other differently. Yes, you have to be careful. We like to repeat letters in physics a lot. Unfortunately.
Yeah. Okay, so 17.4, the answer is A. 17.5, a pitcher contains 0.5 kilograms of liquid water and 0.5 kilograms of ice at 0 degrees Celsius. You let heat flow into the pitcher until there is 0.75 kilograms of liquid water and 0.25 kilograms of ice. During this process, what happens? All right, this one didn't require hunting around for terminology or equations, so hopefully you've got an answer figured out by now. So who thinks the answer is A? 1, 2, 3, maybe 4. Who thinks the answer is B? Who thinks the answer is C? Like 7 or 10 or so. Who thinks the answer is D? All right, so a majority of you said C. Will somebody who chose C tell me why?
Yeah, with the melting the ice.
There's still ice left.
Okay, so the energy is going into melting the ice. There's still ice left, and so
Remains the same until the phase change is complete, like all the way through.
perfect. So combine all those answers together, and that's a complete answer there. So the temperature is going to stay the same until the phase change is complete. Since there's still ice remaining, it would still be at 0 degrees Celsius. Sound good? Oh yeah, Leland?
What if, like, is that assuming that the water is kind of like touching the ice, or does it matter the position of the water compared to the ice? It's just a weird concept.
That is, well, that's something I never thought about. Like if you had a closed container with ice and warm water, but they're not touching, if it would stay at 0 degrees Celsius until the ice completely melted. So the thing would have to be, the water would have to start at 0 degrees Celsius so that both the ice and the water was 0 degrees Celsius. In that case, then, if it was a closed system, then yes, there would be nothing to warm the water. If the water wasn't at 0 degrees Celsius, that's a little bit, I guess that would be a little bit more complicated.
Not
So yeah,
water
but
that would melt from that would be caused from the melting ice. Like if it pooled away from the ice.
okay, so you like had a little funnel. No, I think if it's a closed system where heat can't enter from another source, then that water would stay 0 degrees.
That's so weird.
Yeah, yeah, it's bizarre. So, but you would need some mechanism for the ice to be melting. So if it was exactly 0 degrees Celsius, the ice wouldn't necessarily spontaneously melt. So there would have to be some heat in that system to be melting the ice. And that maybe would affect it if you had like a heat source on the bottom and you had the ice cube over here and then separated like a little channel to separate out that water.
Yeah.
The separate water, I would imagine, would warm up. That would be my guess. But only if you had that heat source that was actually fueling the melting ice cube. So that's an interesting question. I had never thought about that before.
So in terms of global,
It is.
In terms of global warming, the water doesn't increase in temperature yet because there's still ice to melt.
Well, the whole ocean is not 0 degrees Celsius,
Okay.
right? So there's the currents in the ocean that are distributing warmer water, because the water around the equator is the warmest.
Yeah, no, but does the water temperature actually go up in general since there's still
Well,
ice to melt?
you know, the areas where the water is warmest, it'll be warmer. And that warm water is getting circulated to the poles. And so that would fuel more melting because you'd have warmer water circulating than normal. So as it circulates, it's going to cool off. So you're not going to have like, you know, I mean, off our coast, we're pretty close, you know, we're like 45 degrees latitude. Our water is not warm, like 50 degrees Fahrenheit in the ocean. But down in Baja, anybody swam in Baja? I don't know, it's warm. Whatever it is, it's like comfortably warm. So
Yeah, I'm just wondering if you take all the water temperatures in one pot and do the average, does the water temperature average go up? It shouldn't go up as long as there's still ice to melt.
it is going up because it's not, if it was like a closed system where you had a container, then everything would be in thermal equilibrium. But the Earth is not in thermal equilibrium. There are various temperatures throughout, and the currents are distributing those warmer waters to the ice. There you go. So yes, it's not a closed system either, because we're getting heat from the sun. So
curious about because we still have ice to melt.
All right, so next question. 17.7. Suppose that a steel bridge 100 meters long was built without any expansion joints and that only one end of the bridge was held fixed. What would the difference in the length of the bridge be between winter and summer, taking a typical winter temperature at 0 degrees Celsius and typical summer temperature at 40 degrees Celsius? The coefficient of thermal expansion of steel is 10.5 times 10 to the negative 6, 1 over Kelvin. While you guys are calculating, I'll go grab those sheets off the printer. So who thinks that the expansion will be A, 0.42 millimeters? Who thinks it'll be 0.11 meters, excuse me, 0.11 meters? Who thinks it'll be 0.37 centimeters? Who thinks it'll be 0.42 meters? Everybody. And so obviously E would have no votes. So tell me, what equation did you use to calculate?
Changing L.
Uh-huh.
Equals L times alpha. Changing temperature.
Awesome. So we didn't even have to rearrange. So the length was 1,000 meters. Alpha, they give us 10.5 times 10 to the negative 6. Change in temperature is 40 degrees minus 0 degrees. So 40 degrees. There we go. So we get the answer. Everyone said it was 0.42 meters. All right. D.
Do you want to use the linear expansion coefficient though?
In this particular, so volume expansion is valid. I mean, it's going to be expanding in all directions. But if you wanted to know just in one dimension how much it's expanded, that would be the length expansion. Then you can just use the length equation. So if you did the volume expansion, then you'd have to then break that down and say
And the steel was actually 1.2 times 10 to the negative 5th according to that.
1.2.
Times 10 to the negative 5th.
Okay, so they're off by, so this is 1.05 times 10 to the negative 5th. So, yeah.
Or maybe there's some other material in the steel.
But the question of whether to use volume expansion or length expansion, both give you essentially the same answer. It just depends on what information you're looking for. Since we're looking for how much longer the bridge got, and we're only given its length, then we would use delta L equation. Without knowing the other dimensions of the bridge, we really can't do the delta V equation. So, okay, 17.8. Two steel spheres are made of the same material and have the same diameter, but one is solid and the other is hollow. If their temperature is increased by the same amount, how do the two balls' sizes compare after they've increased? Okay, does everyone have enough time to come up with their answer? All right. Who thinks the answer is A? 3 votes. Who thinks it's B? Who thinks it's C? 1, 2, 3, 4, 5, 6, 7, 8. Who thinks it's D? And who thinks it's E? 1 vote. So the most votes came in for answer C. So someone who voted C, want to tell me why you voted C? Gudrun?
The formula for the volume is delta V,
Is
V naught, and then delta T, and there's no M in there. So the mass has nothing to do with it.
okay. So the fact that they have the same outer diameter, if we were measuring their volume, then that wouldn't matter?
Yeah.
Okay.
I thought it was A because of the volume of the steel total. Not just,
Okay.
there's obviously much more steel in the solid one.
Okay. So the fact that if you calculated the amount of steel in each ball, one is going to be smaller than the other. I think that is true. I mean, obviously that's true. One ball has less total volume of steel than the other ball. The answer is C, and the reason is that their outer diameter is the same. And so if you did calculate the change in volume, then this kind of goes back to the question we had last week, that if you look at a solid plate and it expands outward like this, and you had etched in the plate a circle, then that circle shape would be expanded out as well. And so if you think about, if you cut that circle out of the disc, or out of the plate, there is less metal in the, so compared to a plate where this is actually missing. There is less metal in this object, but the expansion happens the same way. So as this expands, it's going to extend outward, and the hole will go outward. It won't go inward, per se. So that's not happening. So it does go outward as it expands. And so the missing chunk would look like the same as the expanded metal with just an etched circle in it. And so kind of using that same logic to a solid sphere and a hollow sphere, the same rules apply. So definitely not necessarily intuitive, but that's how it is. Any other questions on that one? Okay, I think we have one more. 17.9. An architect is interested in estimating the heat loss through a sheet of insulating material as a function of the thickness of the sheet. Assuming fixed temperatures on the two faces of the sheet, which one of the graphs in the figure best represents the rate of heat transfer as a function of the thickness of the insulating sheet? All right, does anyone need more time? Okay, who thinks the answer is A? Who thinks it's B? 1, 2, 3, 4, 5, 6, 7, 8. Who thinks it's C? 1, 2, 3, 4. Who thinks it's D? And who thinks it's E? Okay, so the most votes we got was for B, and then 4 votes for C. So somebody who chose B, why did you choose B?
So the formula is H equals Ka changing T divided by L.
All right, and so we're looking at the relationship between H and L. And so what is that relationship called? Because this is in the denominator. Inversely proportional. Okay, so in math land, if we had an inverse graph, it would be y equals some constant over x. Okay, and so what would that graph look like if we plotted y versus x?
Like the one up there.
Would look like the inverse graph up there? Okay, so it actually would look like that. So we got the right relationship. It is an inverse relationship, but the graph is not something that we frequently have in the front of our brains, you know.
Linear.
Right, I mean, everybody remembers linear. I don't always, I mean, until I started doing this sort of concept of like looking at equations in terms of these 4 patterns, I didn't like always readily remember that inverse looked like this either. So you're spot on that this is an inverse relationship. Remembering what the shape of an inverse graph is, that kind of requires remembering a lot of math stuff that we usually just dump out of our brains. So. Did anybody have issue figuring out what the heck they were talking about? No? I don't know if anybody's going to cop to that, but they don't come right out and say, this is a conduction problem, and you're looking at the rate of heat conduction through a slab of material, and then you're like, oh yeah, I remember doing those problems. So the only hint we have is that term, the rate of heat transfer. And so trying to remember that this thing is called the rate of heat transfer. Well, you might remember because we did it last week, but if I asked you in 3 months, that might be something that just fell out of your head because it's a big long thing. I don't know, that's how I feel. Like I'm like, every time we see it, I'm like, oh yeah, that's a mouthful, the rate of heat transfer. Anyway, if that's something that's tripping you up, maybe that's a good thing to add to your equation sheet. Okay, and I think that's it for clicker questions. Do you guys have any questions, general questions about these review questions or things from last week? You can always save them up and we can talk about them during the review as well. So that's fair game. All right, so we're jumping into our second lecture on thermodynamics. Light's still on, that's good.